இன்னைக்கு ஒரு புது லெக்சர்ஸ் என்ன அப்படின்னு பார்த்தீங்கன்னா electromagnetic induction. Okay, so this is a one shot video about the whole topic. It will be helpful for CBSE board, NEET and JEE. So first of all, ஒரு டாபிக் குள்ள போகிறதுக்கு முன்னாடி அதோட மீனிங் வந்து நம்ம தெரிஞ்சுக்கணும். அந்த சென்ஸ் ஆஃப் மீனிங் எனக்கு புரிஞ்சிச்சுன்னா it will be helpful to cover the topic or to grab the topic fast. Okay, so what is electro? Electro discusses or it means about charges. It means about charges. What is magnetic? Magnetic is nothing but discuss about magnetism. What is induction? Induction is nothing but a process or just we are charging. We have learned that three types of charging are there. One is conduction, induction and friction. So induction is nothing but a charging the body without contact. That word is important. Okay, without contact. Charging the body without contact is actually induction. So we have learned that in electrostatics, we have learned that whenever a charge Q is in the state of rest, it will produce only electric field around the charge. It will produce only electric field around the charge. Then in another case, a same charge particle Q, which is in the state of motion, it will produce electric field as well as magnetic field. So it will produce both electric as well as magnetic field. Okay. So similarly, when a charge particle is in the motion, that is, it accelerates. That is, acceleration is not equal to 0. But in previous case, acceleration is 0. That is, it's moving with a constant velocity. What happens to the charge particle? It will produce electric field, also magnetic field, and radiation. So radiation. That radiation is in the form of electromagnetic waves. So in the form of electromagnetic waves. So we have learned that in a state of rest, this topic we have covered in electrostatics. We have covered in electrostatics. And then about the motion we have learned in electricity. So again about the magnetic field we have learned in moving charges and magnetism. So moving charges and magnetism. So that is moving currents. That is a charge whenever a charge moves with respect to time, it produces a quantity called current. So I is defined as delta Q by delta T. Okay, so this is an average value of current in a given wire. So whenever a current flows, it will produce magnetic field around the charge. So that magnetic field is given by the relation, in a differential form, it is given by the relation. It is mu naught by 4 pi I times of dl sine of angle between them by r square along the direction of normal. So this is explained by the law called Biot and Savart law. Okay. So these are all fundamentals to understand the electromagnetic induction. So there is a question, that is, we can produce magnetic field from electric field. Similarly, the reverse is possible or not? Yeah, the reverse is possible. So we can produce electric field from magnetic field. So by the process called induction. So that is called as electromagnetic induction. Okay. So how we will produce electric field from magnetic field? So for this we have to know about the quantity called flux. That flux is called as magnetic flux. So the flux is called as magnetic flux. So that is related by the term called phi. So to differentiate, there is a difference between electric as well as magnetic flux. So we are giving a term called D. So it is mentioned by the term called phi of D. Okay. So what is magnetic flux? Magnetic flux is defined by the relation, that is, it is some small region. I'm just considering a region that is of area A vector. So magnetic field lines passes through this region, that is our D vector. For example, at this position, the area vector will be n cap. Angle between B vector and n vector is said to be theta. So flux is defined by the relation phi of D is said to be B vector dot A vector. So that is given by the relation. So BA cos of angle between them. So this is said to be your magnetic flux. So magnetic flux depends upon three quantities, that is magnetic field, area, and then angle between B and A. So by varying or by changing these three quantity, we can change magnetic flux in the given circuit. Okay. So by changing the magnetic flux, we can produce electric field. So we can't produce electric field, that is, we can produce EMF. that EMF results in the flow of current. So thereby we can produce the electric field from magnetic field. So that is called by the process of without contact. So that is already mentioned here. That is said to be electromagnetic induction. So what happens by changing these three things? That is comes under the concept called types of EMA. That is types of electromagnetic induction. On what basis we are dividing? So this is comes under types of EMA. Okay. So this is a basic idea about flux. And next thing we'll move on to what is Faraday's model, and then from that Faraday Lenz has developed some other concept. From that we will learn about types of EMI. From types of EMI we will be discussing the whole electromagnetic induction process. Okay. At last we have discussed about flux. That is phi of B is given by the relation. It is dA cos of theta. By changing flux we can produce induced EMF. So that is explained by the experiment called Faraday's experiment. For this you just consider a solenoid connected to a galvanometer. That is, there is no supply. We are just testing the galvanometer. Okay, we are just keeping the galvanometer. Initially, the deflection of the galvanometer will be at the null point because no current flows through the circuit. Okay, whenever you are just bringing a magnet of north and south polarity. So we know that magnetic field lines originate from north polarity and terminate at south polarity. Okay, so magnetic field lines originate from north and terminate at south. The field lines exposed in the coil. Okay, so since the coil's velocity is said to be 0 initially, whenever there is a relative motion between, for example, this setup is said to be in the state of rest. Only magnet starts moving. So initially it is at 0, and then it starts moving with the velocity. That is not equal to 0, some velocity. Okay. Flux. Exposure of flux got changed in the coil. So that results in deflection of the galvanometer. So this is observation actually. So it results in deflection of galvanometer. Also, if you pull the bar magnet away from the coil, deflection gets changed into opposite direction. Similarly, if we are moving with the velocity that is double that of initial case, the deflection gets maximum deflection. Similarly, we are moving with velocity that is v by 2, deflection is said to be in a mild sense. So these are the observations from Faraday's law. So from this we have some conclusion. So that conclusions or those conclusions are called as Faraday's law. From Faraday's experiment, those conclusions are called as Faraday's laws. Okay. So the first law states that whenever there is a relative motion between the magnet and the coil, either whatever may move. Okay. So there will be a change of magnetic flux on the coil, which results in induced EMF. So therefore, whenever the relative motion is there, till that the EMF will be induced. So there is some short statement. That is the induced EMF. The induced EMF lasts as long as the relative motion is there. So as long as relative motion is there. So once there is no relative motion, there is no EMF induced. So this is the first law. So second law is said to be, second law discuss about the induced EMF's magnitude. What is the EMF magnitude? Induced EMF is proportional to change of magnetic flux. That is delta phi b, since it's magnetic flux. So it is delta phi b by delta t. So this is your induced EMF. It is expressed by the term called epsilon. Okay, change of magnetic flux. So we are discussing about some different minute changes. Epsilon can be expressed as it is a d phi of b by dt. Okay, so these two are said to be Faraday's observation from the experiment. Lenz has modified this law, or he made some changes and introduced another concept from this part. This is called as Lenz law. Lenz law. What is Lenz law? Lenz law states that the EMF induced will opposes the cause. What is the cause? Cause is nothing but that is change of magnetic flux with respect to time. So from the statement we can conclude that EMF induced is nothing but negative del phi or d phi by dt. Okay. So whenever we are considering about number of turns of the solenoid, from this we have to give the EMF equation like this. That is negative n times of it is d phi. Again, this is magnetic field. It is d phi by b by dt. So this is your Lenz equation. So that negative sign explains the concept called that opposition offered by the EMF to that of change of flux. So these two laws are very fundamental laws to understand the electromagnetic induction. Next topic, it is types of EMI. It is nothing but types of electromagnetic induction. So we have learned from Faraday's law. What we have learned, whenever there is a magnetic flux, as a magnetic field, there will be a concept called magnetic flux. That is phi of b. If phi of b is said to be constant, there is no EMF induced. Okay, there is no EMF induced, which implies no EMF. Okay. So whenever magnetic field changes, that is your dB changes, which results in d phi of B. Again, field changes with respect to time. Also, there will be a change of flux with respect to time, which results in EMF. That is called as induced EMF. Okay. So how to produce this induced EMF, or what are the different ways of producing induced EMF? That is comes under the topic called types of EMF. Okay. So since we know that flux depends upon, or what is the relation of flux? It is said to be phi of B is nothing but dA cos of angle between them. So from this equation we can conclude phi is a function of three factors. One is said to be B, another one is said to be A, another one is said to be theta. So by changing any one of the factors will results in the change of flux, so that produces different types of EMF. Okay. So in this we will learn about or we will change one factor and keeping other two factors, or other two factors are kept constant. Okay. In first case we will change B, and B will be changed. That is A and theta are said to be constant. A and theta are said to be constant. Then which results in the, D changes, that is your dB changes with respect to dt, which results in d phi of B changes with respect to dt, which results in EMF or EMI. The EMI is called as static EMI. What is meant by static? Static is the coil or anything doesn't move, only magnetic field is changed. So this is called as static EMI. In second case, we are keeping B and theta as constant. Then what happens? Area of the coil varies, which means it starts moving. So it comes under the concept called dynamics. That is your dA by dt, which results in d phi B by dt, which results in EMI. That EMI is called as dynamic EMI. That is EMI produced due to motion is called as dynamic EMI. And then third EMI is nothing but we are keeping B and A as a constant. B and A are constant. Then our angle changes with respect to theta. So this is also a dynamic case, but the thing is, angle changes means it changes in the constant period. So it is called as periodic case. So therefore, d theta by dt changes, which results in d phi B by dt, which results in EMI. That EMI is named as periodic EMI. Periodic EMI. So probably we will be learning in static, there is self-induction and mutual induction. So mutual induction. In dynamic part, we will be learning about that movement, that is motional EMF. And then in periodic part, we will be learning about alternating or AC generator. So from this, we will get some idea about periodic EMI. So this is developed in the next chapter called AC currents. So there we will be learning about depth of periodic EMI. But here we will be getting some ideas about alternating currents. Next we will move on to that static development, that is self and mutual induction. So next topic is self-induction. So what is self-induction? So we know that induction is a non-contact process of inducing a charge. Self means a coil induces itself. So that is called as self-induction by the process of without contact. Okay. So you just consider a solenoid like this. Solenoid connected to a power supply, a strong or whatever it is, a power supply, connected to a key and a variable resistor called as a rheostat. So it is a rheostat and then a key, a battery, a power supply. So this is an inductor of inductance L. That factor we will be learning in self-inductance part. Okay, so that thing we will be learning. Okay, there will be a number of turns, length of the solenoid and area of cross section. Once key is closed, current will flow through the circuit. Current flows through the circuit. What happens to the induction part? So there will be two cases. That is a first case, I is said to be constant. What happens when current through the circuit is constant? So that is, we know that flux means what? Whenever current is there, magnetic field will be there, flux will be also there. So therefore, flux is produced by change of current. So since it has n turns, so n of phi of B is proportional to that of current flows through the coil. So this is for constant current. Okay. So we know that proportionality is removed by the means of constant called coefficient of self-inductance. That is, what is the resistance part of the factor? Opposition offered by the solenoid to that of constant current is known as self-inductance. So we know that again that L is nothing but it is n phi of B by I. So this is your self-inductance part of a solenoid. Since we know that magnetic flux is given by the relation, that is B times of A. For maximum magnetic field, cos of the function is said to be 1. That is, angle between them is said to be 90 degree for perpendicular. So it is given by the relation N B A by I. So self-inductance is also equals to N B A by I. So this is a case when current is said to be constant. In second factor, what happens when I changes or varies, changes with respect to time? Okay, changes with respect to time. That is, whenever there is a change of current with respect to time, there will be a change of magnetic flux with respect to time, which results in change of magnetic field with respect to time and magnetic flux with respect to time. So change of magnetic flux is due to change of electric current. So that is N times of d phi of B by dt is proportional to di by dt. So this is a part obtained when current changes through the circuit. How the changes has happened by the means of rheostat. Whenever we are adjusting the resistance, current will change throughout the circuit in a given interval of time or in a time. So there will be a change of magnetic field which results in change of magnetic flux. Since we know the equation, that is EMF induced is nothing but negative n times of delta, that is d phi d by dt. So this is, you just consider this as equation 1 and this part as equation 2. By comparing these two equations, we will get the result, that is EMF is nothing but negative. Also, the proportionality is removed by the means of constant called coefficient of self-inductance, whatever we learned here. So it is coefficient of self-inductance. So by equating these two equations, we will get it is negative di by dt. Okay. So from this, L is nothing but E, negative E divided by di by dt. So this EMF is said to be a static EMF. So we are just differentiating by the term called, giving a differential by giving S here. So that part is said to be a static EMI part. So whenever current is constant, which implies there is no EMI. Actually, there is no EMI. There is no EMF induced in the circuit. While current changes, there will be a induced EMF. That induced EMF is known as static EMF. It is denoted by the term called epsilon S. So that epsilon S is derived by the above process. So this is called as self-inductance of a circuit. That is, a circuit induces itself while current changes in the circuit is known as self-inductance of a coil. Okay.